Go ahead.
Well, welcome everybody to our May meeting of the IEEE Southern Minnesota section. We have two of my IBM colleagues with us tonight that both work in the area of storage technology. We have Dave Verburg from IBM Rochester and Luis Freeman from IBM Raleigh. And they both work in different aspects of the storage technology. And let me just give you a little bit of their biographies that they put out there. Dave Verburg graduated from South Dakota School of Mines and Technology in 1990 with bachelor's degrees in both electrical engineering and computer science. He's been with IBM Rochester since 1991, starting in disk drive manufacturing, and received a master's degree in electrical engineering from the U of M, University of Minnesota in 1996. He's worked in a variety of roles with IBM in Rochester, has been providing leadership in disk drive quality across multiple IBM brands for the past 15 years, taking on the additional role of solid state device technology selection in the past year. He is currently an STSM for disk drive technology and quality and supply chain engineering, and enjoys working with cross-brand teams to deliver innovative solutions to our customers while improving quality. And Luis graduated from University of Guadalajara, Mexico in 1996 with a bachelor's degree in electronics engineering. He started his career at IBM Guadalajara in 1996 as a buyer for electronic card assemblies for laptops and desktops, and received a master's degree in industrial electronics from ITESO in Guadalajara, Mexico. He moved then to IBM Raleigh in 2000 as a global commodity manager for electronic assemblies, and has worked since at IBM Raleigh in different roles. In 2012, he took on the role of project manager and qualification engineer for storage devices. So with that, I think we'll go into the presentation. Welcome, Dave and Luis, and I'll turn it over to them.
Yeah, thank you, Paul. And thanks to the IEEE Southern Minnesota chapter for inviting us. We appreciate the opportunity. And as we get going, we just wanted to give credit to Jim Gassman, who's given presentations like this in the past, and we, his presentation served as a starting point for us. So I'll make sure I give him a call and let him know that our appreciation. So we'll talk to you today about the basics of SSD and HDD technology. Before I get going, I was just going to display, this is a presentation just to give you education. It's not,
I'm listening.
It's not information that's supposed to be used for any sort of purchasing decision or to hold us accountable for some performance metric or something like that. So just wanted to give that statement here. So what we're going in general, we'll have some breakdown agendas later on, but from an overall perspective, I'm going to talk about market trends for storage first, kind of set the stage. And then Luis is going to talk to us about HDD, the architecture, kind of direction, and some of the challenges. I'll talk a little bit about SSD, same thing. And then there's one of the questions in the market today is, will SSD supplant HDD in the future? And and it already has in some areas, but I want to talk a little about that. And feel free to interrupt with questions, or I'll try to figure out a way to monitor the chat also. If you want to, or Dave and Paul will help us monitor the chat. So feel free, as we go along, to interrupt. It won't bother us at all to answer questions as we go along. So first of all, just to talk a little bit about market trends to set the stage. So one thing that makes this job really interesting, and everybody in IT industry, is we have this digital transformation going on, where we have a data explosion, where now in just a couple of days we generate as much data as was generated all year, and all before, through 2003, everything before that was generated. And the explosion you can see is coming. We have enterprise data that's growing, but we get social media, voice over IP, and some other devices, IoT devices and things like that. And that's a lot of that is all unstructured data, which makes it even more challenging. You have tweets and trade events going on. You can see on the right just some of the information that's being generated. Even just Walmart generating 2.5 petabytes of customer data hourly, and many of us have Facebook accounts. So that's just contributing to a huge explosion in data, and of course then the need to process that data. So it's exciting to be involved in at this time in this industry, and the expectation is it's just going to keep growing exponentially over the next few years. So going down, the other thing that's happening, and I kind of alluded to it earlier, that a lot of the data is unstructured, and so before, when a lot of us were in college, it was, computers were more used for differential equations, which we all enjoyed, I'm sure, but doing analysis of models and things like that. Whereas now, a lot of the computer usage is from a data-centric environment, and mining, AI analytics, and before the bottleneck was more in the CPU and memory, but with the data-centric, it's more in the storage and I/O. And we'll talk a little bit more about that later as we go on. But that's an important bottleneck where there's becoming a lot of, because of the need. Whenever there's a need like this, then we have people that are want to do things to solve that need, in order to have a niche that they play in, or a large part of the market they play in. So that a part of that data explosion, along with the data explosion, what we had, and this was actually a chart that Jim used in a presentation a few years ago to IEEE, that just showed the bridge. Before we had SSD, there was processors and memory, and then disk over here was very slow, and you have even tape slower than that. And SSD was kind of the bridge to be able to bridge between these two. But this need here is becoming greater as we have this data explosion, and the need to build that bridge. To have this. There's not one solution that can bridge all the way across here. So it's that's where we're seeing a lot of growth in the industry, and even with this, there's solutions that are that Luis will talk about where they're working to try to improve the access speed with this, and of course the size. So going to the next page, so like I said, there's a huge growing gap here. Let me go on. So what's happening, and then I'll talk a little about this later again as we get to the SSD portion, but we have the DRAM and CPU over here. You have the HDD and tape on this side of the bridge, and the first solutions that came out were the SSDs with the NAND, but now we're getting 3D XPoint from Intel, or else fast NAND, which actually is just a MLC NAND, which I'll talk about a little later. Versus right now we have TLC over here that are a little bit slower and don't have as good of endurance. And then the other thing that's coming in now, kind of in between the TLC NAND and HDD, is QLC NAND, which I'll talk about a little bit. So there's the area in here. This bridge is starting to fill out with lots of interesting technologies. The ReRAM over here really isn't materializing at this moment. It was something that Mark was projecting, but it really hasn't happened. But there is DIMMs that are NAND type DIMMs that are being used today, like with 3D XPoint or other NAND type DIMMs. So going on, so this is just a picture of that same bridge more in a pyramid mode. But the other part of it, in addition to the speed, is the cost. So your DRAM up here it's costly, and it doesn't have you can't afford a lot and put a lot in your system. So you need this bridge in between, going down to nearline and tape. And this can be a tiered type system, where data is hot data is moved up and colder data is moved down. And the other thing to point out is above this, then this DRAM isn't persistent too, so it can be helpful to have things that are persistent, like the 3D XPoint or the SSDs that will keep the data on a power off, which then otherwise you need some sort of solution to keep power for the DRAM to be able to make sure the data gets written off, and so you don't have data loss. So there's many workloads that can start to leverage this. Some of the AI and cloud type workloads can start to leverage this tiering. So now I'm going to turn it over to Luis to talk to us about HDD architecture. Then I'll come back and talk about the SSDs that I've alluded to.
And you guys hear me okay? Yes, we can. Okay. So the first few slides basically talk about what the HDD is and how it works. And this technology has been out there for over 50 years. So I'm just going to go very quickly through these first charts. I rather want to spend the time talking about the challenges that the HDDs are seeing and the technologies coming out to solve them. So this chart basically tells you what it is. It's basically a device that stores information magnetically. And so go to the next one. Thank you. This one shows all the different components that go on the HDD. You can see on the left-hand side the disks. You can see the actuator on the right-hand side, and then the motor together with the aluminum case on the bottom side, and then the electronic card. So next. This basically shows how the media, which is basically the disk, is split into cylinders, tracks, and sectors. Typical sector size is 512, and more recently we're moving towards 4096 bytes. So next one. So this basically shows how the media is composed of different layers. Those layers vary from product to product. One layer though that you will always find is the magnetic layer, which is where the information is stored. So next one. And this slide shows the actuator. Basically, the actuator pivots around to be able to access all the different tracks on the media. You can see on the the right-hand side, you can see all the different arms with the heads. You usually have, or you will always have, 2 heads per disk, one on the top surface of the disk and the other one on the bottom surface. So if you were to have, say, 5 disks on your HDD, you will have a total of 10 heads on that actuator. Next. And this one shows basically the electronics. This is a block diagram of the microcontroller and how it basically interacts with all the different peripherals, the motors, the actuators, and so on. Next.
Okay.
All right. So recently, about probably 2 or 3 years ago, the nearline HDDs went from being air to helium, and the main reason for that was to increase the capacity. By having helium, you basically you're allowed to have your platters closer together, so you are able to add more disks to your drive, and that also comes with some additional benefits. You're able to get lower power because you have less drag with helium than you have with air, and you are able to run your disk at a lower temperature, or it won't heat as much. And because the drive is hermetically sealed, you don't have problems with particles contaminating your drive. So next one. This basically shows all the different concepts with regards to disk performance. The data transfer rate and the access time are the main terms that you gotta remember. Next one. All right, so let's talk about the technologies that are coming for HDDs. Next slide. All right, so PMR, which stands for Parallel Magnetic Recording, has been out there for many, many years. And it's reaching a point where you are basically not able to continue with this technology because of physical limitations with the way it records. So there are three ways you can approach improving the areal density of the drive beyond the 1 terabyte limitation that the technology has. You can make your media to have grains closer together so that you can record more information on the media. But you run into issues with thermal stability when you get your media, your grain size too small. So the solutions that are out there in play is basically what is called HAMR, heat-assisted magnetic recording, MAMR, which is microwave-assisted magnetic recording, and bit pattern media. And I will go through those in detail in the next slides, but just keep that on the back of your mind for now. And then the other thing you could do is improve the accuracy on your writer-reader actuator. And there are a couple of technologies out there to enable these. One is shingle magnetic recording, and the other one is two-dimensional magnetic recording. And then another thing you could do to increase the areal density is to obviously increase the number of disks on your drive. And for that, as I mentioned earlier, you have helium sealed drives to enable for more disks on your drive. So let's go to the next slide. All right, so this shows basically what the Advanced Storage Technology Consortium published back in 2016 as a roadmap to allow for HDDs to increase capacity over time. And at the time, they were projecting that by 2019, they were going to be ready with HAMR, which is basically the heat-assisted magnetic recording, which will basically allow for to continue the areal density increases. And then after that, they were projecting to have heat dot magnetic recording in play. Well, this projection did not happen. HAMR is actually delayed, and it looks like now it's 2022 when it will become available. And in the meantime, the suppliers are using MAMR, which is the microwave-assisted magnetic recording, to allow for additional capacities. So if you go to the next slide. So this is basically how it looks today. So you can see MAMR came to the rescue. And since 2019, the suppliers have been producing drives using MAMR. All right. So next. All right. This chart basically shows all different technologies that I mentioned earlier. Shingle magnetic recording, basically what it does is it allows you to write your tracks closer together by overlapping one track on top of the other. Now, in order to do this, you got to make sure that you write only once and in a sequential way. Otherwise, if you're trying to do a random write, you are going to basically overlap some of your information, and you run the risk of losing information. So in order to do that, you need the host to be able to do all the management of the writing. So this technology has not been very successful with regards to adoption, mainly because of the requirement for the host to do the management. We're hoping that it picks up in the next year or so. And then the next technology is two-dimensional magnetic recording. This is already in place on the current drives, and this is basically allowing for the reading of closer tracks tracks. So in a way, it compounds the value of SMR and other technologies in place. And then the next technology, which is the heat-assisted magnetic recording. This is the one I was mentioning that was supposed to be available in around 2019, and it looks like it's now 2022. And basically what this technology does is it adds a laser to the head. And that laser basically heats up the media. And by doing that, it basically allows for those grains to basically be able to be recorded without more easily, so that when it cools down again, the data is magnetically fixed on the media. Right. There are some concerns or some challenges with this technology. Basically, the head, because of the laser and all the heat that is produced, has reliability issues, which they are working to resolve. And that's basically what has been delayed the implementation of the technology. Next slide. So here's MAMR, the microwave assisted magnetic recording. And this technology basically does something similar to the hammer. The only difference is it uses a microwave instead of a laser to basically allow for the media to be easily readable. And the main reasons why the supplier switched from hammer to MAMR was obviously because this is a known technology. It has been out there for several years, and it doesn't have any problem with reliability. The cost is about the same as PMR, and is easy to manufacture compared to hammer, where you have the reliability issues.
2 p.m.
You'll have to invest in new materials. You'll have to.
All right, thank you.
You'll have to invest on higher cost than PMR. And then the last one here is the bit pattern magnetic recording. This is basically a change to the media. Today, you have several grains where the information is stored. With bit pattern magnetic recording, you are looking at lithography, so that you basically have one grain per bit. And in order to enable this technology, you will have to have hammer in place so that you can actually address each one of these dots. So yeah, so that's where it is. So that's why you see on that roadmap that this technology is it's probably not until 2025 or not. So, next one. This chart shows basically how SMR works in more detail. I'm not going to go through this because we already talked about SMR. Next one. All right, so another challenge of the growing capacity is basically the Iops per terabyte. As you keep increasing the capacity on the drives, you are still only able to get so many Iops per terabyte. And so you can see as you increase your capacity, your Iops per terabyte decreases. The solution to this, the suppliers are coming with what is called multi-actuator or dual actuator drives. By doing that, you're basically doubling the performance. And you can see in red there how you are actually doubling that, right? And then another concern is the limitation of 550 terabytes per year as the capacity increases. And you can only write so much, right? So dual actuator is also expected to help with that. Next. So this chart basically shows the dual actuator and how it works. So basically, you can see in the center of the slide on that picture, you can see how the actuator is basically split into two. Each one of them works independently of the other. And so you are essentially able to access twice as much data as with a single actuator. And so that's basically how it's done. The benefits of this is that you're able to get a lower power requirement because you're basically, you only have one motor for the disks, right? So you're able to get 14 watts compared to 18 watts that you will need if you have two separate single drives. And then your cost is also lower because if you have both actuators in a single drive, you're essentially saving the cost of one motor to do that. But at the same time, if you have two separate drives, your implementation, two single drives, your implementation for a dual actuator drive is going to be more expensive. So next. All right, okay, so this is basically a summary of how it looks. So the mission critical drives, which are basically 2.5-inch drives, smaller capacity drives, are gonna be displaced by SSDs. There's only two suppliers currently providing the 15K and 10K drives, which is Toshiba and Seagate, because WD has exited the market. We expect that mission critical is going to continue to be available for some years. And then basically the one technology that remains is the nearline drives. We're expecting this to see an exponential growth for the reasons that Dave mentioned earlier. I mean, there's more and more data out there. And even though we have SSDs, they're not going to be enough, right? You're going to have both. We're going to see, we're going to continue to see capacity grow thanks to the new technologies. Hammer should be the one that really brings the biggest of the growths, with Hammer basically being like a temporal bridge until Hammer gets to maturity. And then, we will continue to see SAS and SATA interfaces for HDD, although suppliers are starting to look at NVMe as a potential future replacement. And obviously the Iops per terabyte are becoming something very important. And dual actuator is there to address that. And then from a form factor point of view, the 3.5-inch will continue to be there, as well as the mission critical 2.5-inch drives. And that's all I have. Dave, back to you.
Yeah, thanks, Luis. Good job there. So I'm going to go fairly quickly through some of these topics, but feel free to interrupt me. So this is more of a detailed look at what I'm going to do with the agenda for the SSD part of it. I'll talk about the landscape a little bit. I already talked about that some earlier. Go through some of the basics of SSDs quickly. Jim Gaffman had talked to the IEEE about that a few years ago, talk about management, and then try to spend some time with some of the challenges we're seeing in the industry, and then answer talk about the question that I talked about earlier, and some of the other trends that exciting trends we're seeing, and then summarize. So the landscape, this is another part of the landscape that I didn't talk about earlier, but along with the data exploding, the CPU compute demand is accelerating, but DRAM hasn't really scaled with that. And so that, again, along with what I talked about earlier, with the need for data, again, drives the need for faster SSDs to kind of make up for this. And the Intel is saying that they're seeing larger and larger memory systems to go along with the data explosion we talked about. Again, this is that graph I showed before, just showing the need for these, and I'll talk about this bridge in the middle here. And so, this is just a little bit of historical perspective. So really, the SSD is only, isn't even 20 years old yet. First started in about 2007 with Texas Memory and some other, some other players. So, and now Texas Memory is a part of IBM. but you know, they were, you know, 10 years ago they were fairly expensive. They were quite expensive and had endurance fears. And it's kind of ironic as we look forward now, and I'll talk about that. But we've had, you know, we had an explosion of providers here as it started to go commercial, and still was high cost, but it still had high performance compared to HDD. But then about four years ago, it started to become more mainstream as it became more cost effective. And lately, it's this kind of, you know, its use case is really starting to increase. You know, IBM is, you know, a lot of our solutions, you know, maybe only flash solutions. You know, we do have a lot of HDD solutions for which we'll still need. You know, depending on the you know what the user needs. So we still have a lot of HDD solutions, but we have some solutions that are flash only. So this is a chart that came from Jim that I just updated. Just shows the, you know, what an SSD drive is. Basically, you know, a controller and a bunch of flash plus DRAM, and also we tend to have, there tends to be some sort of capacitance on there to help hold up any data that's kind of in transition. And the form factors are shown here, and I'll talk a little about those in a little bit here. But you know, the starting point here was the 2.5-inch drive that looked kind of like the 2.5-inch HDDs. That was a natural, you know, there was enclosures that could support that. So, you know, there was a SAS version of it. And then once we went to NVMe, which I'll talk about in a little bit as I have time, U.2 was the format there that, again, the 2.5-inch format. There's also M.2, you know, and then there's the, you know, solid state DIMMs that are available. And then the newest form factor that I'll spend a little time on it is the EDSFF that is being talked about in industry, and is in the E1.S. This is a picture of the E1.S, but there's several EDSF formats being proposed. So this is a block diagram. I have it here for reference. I won't spend time on it. It just shows, you know, the controller plus the flash, basically, along with some of the supporting, you know, DRAM and you know, the power caps and some other supporting circuitry. So the other thing that, just to point out, is we have one thing that's key here is we have indirection on SSD, whereas on HDD, you know, if you tell it to write somewhere at LBA, it's a certain point on that drive, and indirection then adds to the complexity, but also, you know, it's there for a good reason, for wear leveling, which actually can help if you have a customer that wants to write to one area multiple times. That's not really healthy for an HDD. But so data, you know, data indirection does make it more complex. You know, we also have think about write endurance, and we also have to, you know, because of indirection, we have to do garbage collection, and you know, to maintain retention, there's read disturb has to be considered, and you know, there's also potentially write throttling has to take place, although you know, that's not needed in a lot of cases in order to meet the drive rates per day, and for power management and heat management. But the other thing that has to happen is there has to be bad block management, and so I'll reference this a little bit later when I talk about some of the challenges. But it's, you know, there's less spinning parts, so the, you know, the expectation would be it's better quality, but it's a more complex device from a, you know, from a firmware and a device management perspective. So the one thing I referenced a little bit was wear leveling. So with the, you know, one problem with NAND is if you repeatedly write to a particular location, it causes wear. And this is just a chart actually that Jim had used. But so what you have to do is do wear leveling to move data around. So if a customer is writing one location a lot, you have to move it to another location to extend the life of the flash, so that you evenly wear basically the flash. And there's two types referenced here, but you either have to move it, you know, when the data is coming in, or you have to move cold data, because if the cold data sits in one spot too long, then that part of the flash will, you know, will have more writes available than one that's being written a lot. So you have to, you know, there has to be algorithms to move that data around. The other concept is garbage collection. And I'll just quickly touch on this. This again was a chart from Jim, but just to refresh your memory, so data is coming in. This is the green data, data coming in, and then there's some data that becomes, unneeded by the system, so you call it garbage. And then at some point, then here you're starting. What the system has done is move the good data from this block over here, and it's and it's actually starting to consolidate as you go along. So now all the data at this point is consolidated to one area, such that you can then erase this set of cells and have them available. And it's a little bit more complex than that. So you got to keep track of, okay, which one to use next, which one has the least amount of writes, etc., to be able to manage that. And then the other related to that then is write amplification. So one thing that happens is, in order to meet retention, you allocate actually more flash than the user can see, and that's called over provisioning. And so if you have a lot of extra flash, then your over provisioning is, let's say 28% would be a typical 3 drive write per day flash. Then you have you have 28% free. So this parking lot picture kind of would explain it then. If you have more spots free, it's easier to consolidate your data, and you don't have to. Then if you don't have very many spots free, then your write amplification is higher. You're doing a lot of writing as you're doing your management of the flash. That's not customer data, it's data that you're writing. So that's what, data written to the flash versus data written by host. If you don't have a lot of over provisioning, you can get a lot of high write amplification and use up your flash sooner. So this tends to be more with the lower drive write per day drives. So I'm not going to spend a lot of time there, but I just want to highlight that is a part of complexity with SSD. And so the other thing then, related to that is endurance. So another concern people have is, okay, how long will my drive last? And you don't actually have to understand under the covers, just have to manage, the drive write per day advertised by the supplier. And, we have some customers, they'll say, oh, how many times can our flash be written? And they think they need to understand this part, but the key is to understand what's the drive write per day. And what that is how many times can you write the whole device each day typically over 5 years. So, a read intensive drive might be one time you can write the whole drive over the day versus some of the solutions that have previously were offered were 10 drive writes per day. And then some of the server class memory or like Intel 3 class line is maybe 30 drive writes per day. So, and there's a lot of factors that go into that. I think I'll move on just from the sake of time. Then because of that, then firmware architecture is one of the challenges for SSD, just because of all that complexity I talked about. So I'll reference that. But another challenge is just, the continued innovation in order to drive the capacity increases is a challenge. Data retention is another challenge, especially, it's one of the new challenges during COVID, and I'll reference that. We have another thing that's crept up that you wouldn't think would necessarily be a challenge related to SSD, but I want to talk about is the GDPR, or personal, identifiable information, that's becoming more sensitive for people. And the fact that in reality, though, we really want to be able to, have these drives come back and be able to reuse them from a green perspective. And then we also are seeing some interface changes and some, diversification in the types of interfaces potentially being proposed. So, from an architecture perspective, I talked about all the challenges with, with some of the wear leveling and garbage collection. One thing IBM is doing is we have a quality summit process to work with the industry to address firmware quality. So, and we don't just talk about firmware quality, we have other aspects as a part of our summit process, but it's a way where we kind of standardize and make it kind of an engineering way to go through, step by step through the process and give the suppliers scores in each of these areas and tell them ways they can improve. So that's one thing that we're working on from a firmware quality and some of the other areas of flash. And we have seen good results as good improvements as a result of that. So we do that yearly with our suppliers and then work with them to improve. And actually, our suppliers are actually, if they're not, we have a limited number of people we can invite, and if they don't get invited, they're actually, because of the usefulness of it, they they complain. So it's been a good success for us. The other thing I mentioned earlier was NAND flash evolution. So this is, you know, previously there was, you know, a floating gate 2-dimensional NAND. And then a lot of suppliers have went to a charge trap flash, which is, you know, has a smaller profile. There's some that still use floating gate for certain types of applications and certain suppliers. But the innovation here happened was when they went to 3D, where so they turned this kind of, you know, and put this, you know, the control gate and insulator kind of inside into a little donut type thing, and then stacked them on top of each other for 3D NAND. And so you can actually, you know, you have a lot more density. And so, you know, that actually happened in 2012, but as you go out now, it's been accelerating. And we think it's, you know, by next year, currently we have the 90 to 120 layer available. But, you know, by, you know, next year, we expect to have 200 plus layer, potentially, you know, 2025, 2026 timeframe, there could be 500 layer. And there's a lot of challenges with doing that. So it may not happen, just like the hammer didn't happen for HDD. But I'll come back to that. That could help drive the cost down too. But as you do, increase. And one thing we're also seeing, and this is a number of bits per cell too. And so as you do increase that, then you have, we also seen that, you know, the amount of programming erase cycles go down that they can take, and also ECC correction, you know, the requirements going up. So that also adds to some of the challenges. And I referenced the different flash types. So, you know, initially it was the SLC single level, and then, you know, single level cell. And then we went to MLC. Now we're actually doing TLC, and this chart is a little deceptive in that it's not like you have 16, you know, times or 8 times the space as you did with SLC. You can see the chart here. You know, so there's kind of it's maybe one, you know, TLC is maybe 1/3 versus 1/4 of QLC, and PLC is 1/5 as far as the cost per density anyways. You know, so it's not like you get 1/8 of the cost or 1/16 here, but it is jamming more bits per cell in there, so that you can, you know, so we can have more data in a smaller space, along with then this the stacking that I talked about, being able to do, you know, or do multiple layers of the NAND. So currently you know, we use the, you know, MLC for the fast NAND, and then TLC is our, you know, is the more traditional SSD right now, that's being used. But as we move to potentially QLC, and there are QLC solutions out there, you know, the write time per page increases while you know, the read time also increases, but your cost per density goes down. So there's kind of a trade-off there. But I do expect us to start to use QLC more in the future. And in fact, the flash core module from IBM uses QLC. So another concern that I talked about was retention. And I mentioned that this is a concern during COVID. And so what happens is, you know, NAND, you know, is a memory that stores electrical charges, where on HDD, you know, it's you know, you have the magnetic there, and you can turn HDD off, and maybe, you know, 3 or 4 years later, you can still get the data. Actually, I've done that at home and got pictures off old HDDs. But on an SSD, that won't work. You have to be able to, if you can't power off. Once you have a SSD with data on it, you know, the standard is you can only power it off for 3 months at 40C, and that's at end of life. A newer drive will do better than that. But we have had customers that have, because of COVID, they powered the systems off for a time, and came back, you know, several months later, and some of their data wasn't, you know, as available as we would like. And you know, the reason, and there's a lot of factors that play into it, and I'm not saying here that this applies to our drive, but, you know, a lot, if you have a high temperature in your data center with the drive powered off, it really limits your endurance. And actually, the temperature that the drive is running at the time it was written also plays in. But you can see here, client client drives do have a longer retention the spec, but enterprise that are used is typically around 3 months. And we usually advise customers to do it, to power on a system sooner than that and not push the envelope. So that is one of the SSD drawbacks that, like I said, during COVID has kind of come up for some customers. Another thing that's interesting that's happened is GDPR requirements. And you can see a lot of you probably know about GDPR, what it does. It's good in that it's made people aware of personal data. And one of the, but some of the challenges is that, it's hard for business to know exactly, okay, where is that personal data? Do I have some of this European customer data on my drive? Do I know, who has access to it? Do I know where that data is and has it been erased? And so one of the problems because of that is businesses aren't returning, are less likely to return their disk drives, because they don't want to violate GDPR, which is a good reason, but that's not as green because we can't reuse those. And so one of the, we need to be able to have, rely on encryption and improve data deletion services. So kind of related to that, traditionally with HDDs, you could just degauss them. Now that made them pretty much unusable too, although you could still recycle it, but it damaged the head. But that's ineffective for SSD. Shredding was a possibility, but with SSDs now, it's a smaller and smaller data. You may not be able to show that all the data is destroyed, and it's also really not green. Encryption is a good solution, but sometimes that we need to be able to validate that it's been enabled and that the encryption keys have been erased. So that's a challenge that IBM is working on some solutions related to blockchain to see if we can really track that data has been erased. And overwriting is difficult to do with SSDs because of the indirection that I talked about before, and the fact the user doesn't have access to all the data. So that's another challenge. So there is NIST standards that that are being that have been issued. I list them here, and destroy again is similar to the shredding back here, and it can be other methods, like melting, but it isn't really clean green. So these two, ideally we would be able to have make sure we have leverage these two types of solutions, and then be able to, along with encryption, and be able to track that the data has been erased, so we can have proof and be able to leverage the drives. We do, Seagate is one of our biggest HDD vendors, and they're on board. They want to be able to, they feel they're the best people to recycle their parts. They know what's there and what what it's made of and where they can use it. So circularity is the concept here, and it's important. It's good for us to be able to be good stewards of our environment. So the last question one question I want to touch on that I've been teasing you with is when will SSD displace nearline HDD? And we need to look at 3 different areas here. And so first of all, looking at performance. So the TLC, the 3 bits per cell flash, you can see the performance here compared to QLC and nearline flash. So the question is, well, when or will QLC displace nearline? And it is slower, especially with writes, than TLC. But it's meant, the idea here is that, and a lot of nearlines is more for storing, storing data that might be read, like media streaming or things like that. So it's not too far off, especially with some of the random workloads. But it doesn't have as much endurance as QLC does, or potentially retention. That's still being worked. But the one thing that's interesting is, Louis talked about the 550 terabytes per year. That actually, nearline HDDs actually have less endurance than a QLC drive would, even though we don't typically, that's not something that's on the top of people's mind. And because it's slower than QLC, there, you may not have a chance to hit this, but we have seen customers being able to leverage their nearline drives more. So that is a comparison. And the interesting thing is now SSD has surpassed the capacity of HDD also. So will it happen? I guess one of the things, this is a chart that Jim showed a couple years ago, that showed, SSDs and the trend down, and this came from IDC in 2017, and it was projecting that SSDs would, this bottom line here, the gray line, is the 1 terabyte per day, or actually the SATA, it's a SATA SSD, and the blue line is the one, is would be, I think, the 1 terabyte. But anyways, these drives are showing as crossing the 15K HDD line, and they don't really need to cross in order to, because of the performance, being better, they don't need to necessarily cross it in order to displace them. But this was just a projection that they would be, about 2x of 10K and about 8x of nearline by 2021, and crossing the cost of HDD. But the interest, and because of that, there's people that are saying, okay, then by 2026, there's gonna be a crossover point, and I'll obviously be displacing, HDDs. But what's really happened is it hasn't. This is the 1 terabyte per day HDD, and this is the 15K, RPM HDD, and it came down here, but because of, potentially flash shortages and other factors, it really hasn't crossed. So it came down here, but it didn't make this, it hasn't crossed yet. Now I do expect, again, with QLC, that we'll be able to then start to come down again. But you can see we're still 8 or 9x difference from nearline, and really I think to start to displace it in some applications, it needs to get down here, 4 to 5x of nearline. So we'll have to watch that. I think it will have some applications, but just a reminder, we have the data explosion that we talked about. So we still, with this data explosion, I think there's going to be a strong need for HDDs. And in fact, HDD shipments have been growing. The nearline HDD shipments have been growing. This is exabyte shipped, probably even faster than SSDs, in the past few years. So it hasn't happened yet. And so I think there's still going to be a place for both. And now the thing to watch though will be, when will we get to this 500 plus layers, and what will the cost be? And will suppliers be able to, actually produce this and be able to manage it? And so that's, that'll be a question that we'll keep an eye on. The other thing I'll just talk on briefly, I think, and I'll probably end there, is that, that NVMe is our new, is a new standard for SSDs that really, SAS was more for HDDs, and this NVMe is a faster standard that allows us to really leverage the power of SSDs. And it was available in different formats, but it's kind of an industry consortium. And the three main ones that we're starting were adding card, U.2 and M.2. But this one is the most common right now, the U.2. It's kind of like a shape of a 2.5-inch SSD, but it's the most common. M.2 is used in cloud yet. But the one thing that we're seeing here is that these are the speeds, the interface speeds for NVMe, the yellow here. And as we get into 2022, there's Gen 5, which proposes 126 gigabytes per second, which may not be possible with U.2 and U.3. It's probably possible with U.2, but U.3 is also uses that interface and allocates some pins to other things. So that may drive us to go to EDSFF, which I summarized on this page. But there's a lot of different form factors here. There's a 1U that's being used, starting to be used today now with cloud. It's a smaller form factor, 1U short. There's also a kind of a 2U called E3, but there's short, there's long, and there's narrow and wide. So there's multiple different configurations that can be used here. So the industry is still working to converge on that, but that because of the speeds here coming in 2022, I still expect U.2 to have a long life, but we may have for the faster speeds there may be some EDSF form factors that emerge. And so I think I'll stop there. There are some charts on computational storage for the future, which is an interesting concept, and also NVMe or Fabric. But the storage industry is moving at a fast pace. It's really exciting with AI and cloud applications. We've seen dramatic density and performance improvements. But HDD innovation is continuing, like Louis said. So on Flash, we're seeing the 4-bit cell QLC move into the enterprise space. So it's it keeps things interesting as we monitor where that's going to fall and what if it can meet some of our needs. And then there's some new technologies that are obviously coming into play in that bridge that I mentioned before. And we're going to have continued innovation to meet the AI and cloud needs. So any questions?
I had a hard drive question.
Sure.
So this wasn't something you really touched on, but hard drives are devices that are sensitive to vibration and also produce vibrations. And as such, a lot of manufacturers will rate how many of a specific type of hard drive you can install in a system. What is the physical difference between a drive that's rated for 2 drives in a system versus a drive that's rated for 40 drives in a system?
So let me first say that's a good point. And actually, Louis talked about narrowing, the need for putting platters closer together to be able to fit more space in, and so vibration, they're becoming more sensitive to vibration. So I guess Louis, I don't know if you know that if we typically, I don't think we typically work with the drives that are just 2 per system. It likely has it may even be related to what trays you put on the drives. IBM has a pretty extensive vibration department and a tray design department that helps do things with our systems to help mitigate cross HDD vibration.
Yeah,
but
it's probably more related to the system than it is to the drives.
Yeah, because I don't think we have any systems where it's limited to 2, but that's a good point. Vibration is a concern, and it's a future. We didn't get a time to talk about it, but it is a concern for the future. And one thing that's really interesting is there's even, external vibration can be concerned. That we've had, some fire suppression systems that get tested can even cause HDDs to have problems because of some of the acoustics with, I think usually it's the alarm that going off, but it is something that it's good for customers to ensure that they aren't causing external vibration. Any other questions?
All right, I got one in chat to me. From a user perspective, how do I know if my SSD should be replaced? Is there a particular piece of the acronym SMART data I can look at?
Yeah, that's a good point. Yeah, it's a good question. So with SSDs, there's different ways with SMART, but depending on the SSD drive. But first of all, if you have a 10 drive per day drive, and you haven't had it for 5 years, it's not likely that it needs to be replaced. So that's the first response. And then with 1 drive per day drive, there tends to be fuel gauges that show, there's typically a SMART parameter you can look at that shows the % used. And that's what you want to do is catch that before you get down to, before you have 10% life left, basically, or have 90% used. So that's the key thing you want to watch is and even before that, how much are you using it each month? Let's say daily it might vary, but you do want to. That's probably the key there. And like IBM will have SMART warnings when you get down to when you get down to, let's say, 10%, or I'm not sure, depending on the system, when you get down to a certain percentage, we'll warn you that, look, drive is getting to the point where you're running out of endurance. But that is something you should watch. I don't know, Jeff or Luis, if you have anything to add on, Jeff Repke or Luis, if you have anything to add on the parameter.
This is Jeff. If the question is coming from the perspective of laptops and personal computers instead of enterprise, it's a little challenging. What I do know is that a lot of the storage manufacturers, Micron, Seagate, and WD at least, and maybe others, have utilities that you can download and install that'll run under Windows and or Mac, the Mac OS, that will go in and read those log pages that have the smart data. And the operating systems might be doing it and it might not. It kind of depends on their drivers, whether they're monitoring that, and you'll get a warning from, you know, Windows or the Mac OS, but a number of the suppliers have utilities you can install, and then it'll allow you to go look at that smart data, and those utilities also allow you to update the firmware on the drive, and you can do a lot of other things that, you know, can erase all your data, so you need to be careful too.
Great. Well, thank you, Jeff. I'm glad you joined. So good. Okay. So any other questions?
All right, I got another one from Vince. The speakers talked about data security specifically for SSD solution. Is one solution heating the drive and waiting kind of the accelerated life process to ensure data is deleted and erased?
Oh, that's interesting. Yeah, that's interesting. Well, so the problem is, I think you'd have to, you know, if the drive was pretty new, you might have to wait a long time. So, but yeah, that I haven't thought about that, but that could potentially be that's interesting. You know, just take advantage of the fact that of the retention issue. So yeah, that's an interesting proposal to, and I think the problem would be is some cells may be kind of stronger than others, so you would lose, like, you know, 90% of your data, but that last 10 might be challenging. But I could ask the suppliers about that. That's an interesting concept.
He adds, please add me to the patent.
Sounds good. and who was that was speaking?
That was Vince Winstead.
Thank you, Vince. Yeah, I like how you think. That's an innovative way to think. You use a weakness of the drive to our advantage. So, any other questions or comments?
I guess I had one from myself with what's the phrase, single event upset or those sorts of things affecting DRAMs and SRAMs as NAND flash continues to shrink. Is that a problem with that?
Sorry, for some reason I muted. But yeah, I think it. So I'm not a flash expert, but I think that is a concern that you know, with that we need to make sure we manage for QLC. I know, you know, IBM does use QLC with our FCM drive, and we do have a lot more flash management that we need to do as we have smaller drives. So yeah, so I think you know, now we do, you know, we do have you know, ECC to be able to try to prevent single event upset, but I do think it's you know, it can be more of a challenge.
Okay. Any other questions? That's all I see in my chat box.
Yeah, good question. If
not, I guess I thank you guys for your presentation today. Always good to get these updates on the state of the technologies. I guess if anyone does have any questions afterward, you can feel free to email those to me, and I can pass those on to our presenters. Again, thanks, Dave and Luis. Appreciate your time tonight, and thank the rest. I thank the rest of you guys for attending. One last reminder is that we do have again one final presentation for the spring here next Monday, and you should be seeing a meeting announcement coming out shortly. That's it for tonight. Thank you very much.
Okay, thank you.
Thank you.
Thanks.